Topic 1.4, Logarithmic Functions and Models. Now we want to compare an exponential and a logarithmic function. Let's go back to exponentials. When we graph an exponential, the basic exponential, we'll find that the graph is slow to rapid growth. Again, this is slow to rapid growth. And three examples of functions that are exponentials would be an exponential with a base that is 2, an exponential with a base that is e, and an exponential whose base is 10. Now e is a constant. It's irrational, but it's a constant. It's about 2.17. There are more numbers, but this is about what we call it. Oh, sorry. Let's say about 2.7. Sorry. So whenever you hear me say 2.7, there are more numbers, but this is what we call e for now. Okay. Now, the logarithmic function is based off the exponential function. So, if a logarithmic function, you input 0 and you output 1, let's say we're using this one right here, and then we input 1 and the output is 2, and then we output, let's say, input of 3 and the output is 8. Okay. The logarithmic reverses all the input and output. So instead of 0, 1, it'll give you 1, 0. Instead of 1, 2, it'll give you 2, 1. Instead of 3, 8, it'll give you 8, 3. And the graph will look like this. The graph of a basic logarithmic function is rapid to slow growth. Rapid to slow growth. Let's make it a little better. And it reverses all the original exponentials. So if an exponential produces a 0, 1, the logarithm is going to have a 1, 0. If the exponential produces a 1, 2, the logarithm is going to have a 2, 1. And if the exponential produces the number 3, the 0.38, the exponential is going to produce the 0.83. And the functions will look like this. F of x equals log of the base that it came from, the base exponential that it came from, of x for the input. So if you input a 1 into this, the output will be 0. Whereas you input a 0 into this, the output will be 1. Next, the inverse function for f of x e to the x will be log base e of x. And the inverse for f of 10 to the x, be f of x equals log base 10 of x. Now let's look at the property of logarithms. There are two basic logarithm properties that will need to be memorized. The first one deals with an equation. If your problem starts off as an exponential, where you have a base raised to an exponent, and together the base and the exponent give you an answer, here a. The logarithm combines the base and the answer to give you what the exponent was. So when you rewrite this as a logarithm, you keep the base, so this will be log base b. The answer over here will go here, so the base and the answer are now together, and they will all equal whatever this exponent is. This is how we convert an exponential into a logarithm. And if we wanted to convert a logarithm into an exponential, we would take the base here, write it big there, and then take whatever's over here, write it as the exponent, and whatever number is here goes across on the equal sign. So that goes there. So again, these two show up on the same side, and this one, this whatever is here, is equal to. So for instance, if we had a 5 to the second power, which is 25, the logarithm for this will be log base 5 of 25, and that will equal 2. Another example, if we had log base 4 of, let's say, 1 equals 0, we could turn this into an exponential by saying the base will be 4, the power will be 0, but the answer here will be 1. 4 to the 0 equals 1. Okay, the second property is this. A logarithm with base b of x. This is called the change of base formula. We can change any base from, let's say, b to another base, let's say a, by using this. Log base a, the new base, of x, divided by log base a again, but the number that we put in is the old b. This changes the base. The reason why we want to change the base is because our calculator can only do 2 bases. Our calculators can do a base when it's e, and our calculators can do a base when it's 10. The button for the base when it's e is ln, and the button for base 10 is the log button. So our calculators can only do base e and base 10. So if the original problem is in base 2, your calculator cannot do it. So we would have to use this property to change the base, let's say, from 2 to either e or 10, so that we can actually use the calculator to get the value of the logarithm. Okay, we're going to solve for x on number 1. Number 1 is going to take about 1 step to get the x by itself and get the 4 away from here. So we're going to use a logarithm that's going to combine the base 4 and the answer 3, and then set everything equal to x. So converting this to a logarithm, we have log base 4 of 3. So these two combine together, and then those will be equal to the x. Now, there is no button for log base 4, so we're going to use the button for log base 10. So using the button for log base 10, we need to use the change of base formula, which is that second property. So this will be log base 10 of 3 divided by log base 10 of 4 equals x. And now, to get log base 10, you will press the log button, and then you will type in 3 in close parenthesis, then hit your division button, type your log button again, then type in 4, close that parenthesis. Then when you press enter, you're going to get the value 0.792, and that'll be your approximate answer for x. Next, we want to solve for x. There are 3 things that we need to get rid of: the 6, the 1, and the 3. Once those 3 things are gone, we will have x isolated. So first, let's get rid of these 6 by using the property that removes the base and turns this into a logarithm. So this will be log base 6 of 30, and that'll equal 3x plus 1. Okay, now the 6 has been removed, and we now only have 3x plus 1. Next, I want to get rid of the 1, so I'm going to subtract 1 from both sides. So this is now log base 6 of 30 minus 1 equals 3x. So that's 2 down. We just got rid of the 6. We just got rid of the 1. Now we have left this 3. So I'm going to divide both sides by 3. And now we have x. Now I'm going to use the change of base formula for this one. So for the calculator, we're going to put inside the calculator, let's say we're going to change the base to a e. So this will be log base e of 30 divided by log base e of 6, subtract 1, all divided by 3. Now when you put this into the calculator, you're going to have to open up a parenthesis and then type in your log base e. And then 30 close parenthesis division. This will be log base e 6 minus 1, and then close the numerator and then divide by 3. So it'll actually look like this when you put it in. Open parenthesis, ln button with a 30, close parenthesis, divide by ln button again, put in the 6, close the parenthesis, subtract 1, close another parenthesis, and then divide all by 3. Once this is done, you're going to get 0.2994, the exponent. And this is approximately x, or should I say for the x. Number 3, we're going to solve for x, and there's a number of things that need to go. First, before the base 1.5, the negative 1, and then the 2, and then we'll have x by itself. So it's a minimum of 4 steps to get rid of these elements so we can isolate the x. So first, let's get rid of the 4 by dividing both sides by 4. And we get 1.5 to the 2x minus 1 power equals 2. So that was step 1, getting rid of the 4. Step 2 is getting rid of the base of 1.5. I'm going to put the logarithm on the other side and bring down the 2x minus 1. And on the other side, I'll put the 1.5 as a base of the log and the 2 together. So log of 1.5 of 2. Okay, that's 2 things down. Now we have the 2 and the negative 1. Let's get rid of the negative 1 first by putting a positive 1 on the other side. So log base of 1.5 of 2 plus 1. And the fourth step is get rid of the 2. We'll divide both sides by 2. And we end up with x equals log base 1.5 of 2 plus 1, all divided by 2. Now I'm going to use the change of base formula to change this from a 1.5 to a base of 10. So that will be log, which is base 10, of 2 divided by log of 1.5. Again, log is base 10, and then plus 1. And we'll divide that all by 2. And in order to put this into the calculator, we'll have to start this with a parenthesis and end this with a parenthesis before we divide by 2. When we're finished with this, we'll have 1.355 approximately. Part 4, number 1. We want to find the formula that represents the half-life of 28 years using the exponential rate form, which is the time and the amount as input and output. So let me review a little bit. We have been using the exponential form where y equals a and b raised to an x. And we had to find the a and the b in order to find the formula using input and output. Now with the rate formula, we still have the a, but the b is now e. And the unknown is a rate or constant on the x. So instead of finding the a and the b here, we have to find the a and the r. Alright, so let's find some input and output to use to get this started. Now we are told that the input is time and the output will be the amount. Okay, so when the time is 0, I have my entire amount or the entire quantity. So I'll say at time 0, we have the entire quantity. I'll put the Q for quantity. 28 years later, the quantity will be half of whatever it was. So 28 years later, we have 1/2 the quantity. That's what half-life does. When you get to whatever the half-life years are, the quantity is half. So let's use this with the y equals a e to the r x power. Y equals a e to the r x power. This is my x, this is my y. So y becomes the quantity. And e to the r times 0 for x. And what we get is q equals a and e to the 0. Well, e to the 0 is 1. 2.7 to the 0 power equals 1. So this is q equals a times 1. And so we have just found a to equal q. So we can take this along with this x and y and put it into this value here. So y is half of the quantity. A is q. R is unknown. And x is 28. Okay. Now we're going to solve. We're going to solve for that r there. The way that we're going to do it is that we have to get rid of the q, then the e, and then the 28. So about 3 steps. So getting rid of the q, we'll divide both sides by q. And that gives us 1/2 equals e to the r times 28. Next, we'll get rid of the e. We'll get rid of the e by turning this into a logarithmic problem. So we'll put the base here together with the answer 1/2. So log base e of 1/2 will now equal r times 28. Now there's one step left to get the r by itself, to divide both sides by 28. So I divide both sides by 28, and now I have r. Now, log base e in the calculator would be ln. ln is log base e. Then we're going to type in 1/2, and then divide that answer by 28. And this will give us our r, which will be negative 0.248. So negative 0.248. That's our rate. So now that I have my a and I have my r, I go back to my formula and I put all that in. Instead of using y, I'm going to use the amount, which is, let's say, a equals a, which is q, and then e, r, which is negative 0.248, and then the time will be my x, so I'll put t. And so this is the formula that gives you the half time for this quantity. Next, if blood alcohol starts at 200 and decreases to 150 in 1 hour, find the rate of alcohol decay. So we want to find the rate of alcohol decay, which is the r. Okay, so it means we have to use this form right here, which is y equals a e to the r x. And we're looking for what r is. Okay, so the input here will be time, and the output will be the blood alcohol. So we'll say BA, blood alcohol. We're told that in time 0, there's about 200, the measurement of alcohol in the blood is 200. Then we're told that 1 hour later, we're at 150. Okay. So between these two, we want to find the rate at which it's decaying. So I'm going to put, let's say, y equals a e to the rx here, and y equals a e to the rx there. The 200 will be my y value, and my 0 will be my x value. So 200 goes here, equals a e to the r times 0 for x, and we get 200 equals a e to the 0. E to the 0 equals 1, and we have that a equals 200. Now we're going to take a equals 200 along with x equals 1 and y equals 150 and put it in back into this equation. So this will be 150 equals 200 e to the r times 1. Okay, now we're going to solve for r. It'll take about a couple steps. We need to get rid of the 200 and then the e. So we have 150. Well, let's divide everything by 200 first. Okay. And what we get is, I think, 3/4 here, and e to the r, because 1 times r is still r. Then let's convert this by putting the answer here, 3/4, together with the base as a logarithm. So log base e of 3/4 will equal r. Log base e is the same as, we get that by pressing the ln button and then typing in 3 divided by 4, and that will give us our rate. And the rate ends up being negative 0.288. And that's the rate at which the blood alcohol is declining. About 29% loss every hour.